Hi, I'm Chris Scott. I'm recording this on the 11th of December 2024, which is the 100th anniversary of Edward Appleton's experiment that proved the existence of the ionosphere, and I'd like to talk to you about it. Well, radio was already in widespread use in the 20s for communications, and on December the 12th, 1901, Marconi had conducted a famous experiment in which he had transmitted a radio signal from Poldhu in Cornwall to Signal Hill in Newfoundland. We've got some photographs here showing the transmitter masts in various configurations, the transmitter buildings, and inside the transmitter buildings, the transmitting equipment. Well, why was this achievement so remarkable? Well, Google Earth shows that the remains of Marconi's transmitter is still visible at the site. It's that circle in the field, so sort of bottom left of the picture there. And you can also see the remains of his building. On December 1901, Marconi arranged for the Morse code letter S to be transmitted at a known time, and he listened in at Signal Hill in Newfoundland, over 3,600 miles away. We can go and take a look what sort of distance that would be. So we'll go up from Poldhu in Cornwall and across the Atlantic and down to Newfoundland in Canada, where Marconi and a couple of his colleagues had positioned themselves to listen into the experiment. This is Signal Hill, although I don't think the car park was there in Marconi's day. And if we go back up again to look at the view from space, we can see just how remarkable an achievement this was. This had sent a signal around a significant fraction of the world, and proving that this was possible opened up communications for many different applications. But people still didn't quite understand why it happened. So let's have a look at that geometry. If you broadcast your radio signal, it will go out in all directions, but the path that we're interested in is the path that goes between Poldhu and Newfoundland. But light travels in a straight line. People knew that at the time. So what was causing it to bend around the world? Well, there were various theories. Some people thought that the ocean had some kind of electrical conductivity which made the radio wave bend. And there were also a couple of scientists, Kennelly and Heaviside, who had both proposed the existence of a radio reflecting layer in the upper atmosphere generated by the sun hitting the Earth's atmosphere and electrifying it. And if you had a reflective layer, then you could expect your signal to bounce and go over the horizon. But the existence of that layer was very hard to prove. And it wasn't until Edward Appleton considered this in the 1920s that the mystery was finally solved. Now, Appleton was interested in why radio signals faded in and out at night. And there's a plot here from the paper showing just after sunset, you can see the strength of the signal getting more intense and weaker and more intense and weaker over quite an irregular pattern. And Appleton thought that this was because there must be two paths that the radio signal could travel in, one slightly longer than the other, and so that when they both arrived at the receiver, they were out of phase with each other and they interfered with each other and made the signal fade in and out. And so he proposed that these two paths were a path along the ground and a path that was reflected off something in the atmosphere. He called these two the ground wave and the sky wave. So in December 1924, Appleton arranged for a friend of his to transmit a known radio signal from the transmitter at BBC Bournemouth. And there is some footage that exists of the transmitter at BBC Bournemouth. And here we have some of the people moving around. You can see it's on the edge of a housing estate of bungalows in the background. And it's a fairly modest building, but it has some big antennas from a range above it. And we can see here a photograph of the BBC Bournemouth hut. This is the British Broadcasting Company at the time. And the length of the wires were needed to transmit the radio frequencies that they wanted to travel long distances. And there's a picture there also of the inside of the transmitter hall. Well, while the BBC Bournemouth buildings don't exist anymore, the plans of where they were on Bushy Road next to the cemetery still exist. And we can use the power of Google Maps again to overlay those and see what the site looks like today. So the site has been overbuilt with bungalows, but we can use the power of Google Maps once again to fly with the ground signal along the ground from Bournemouth to the University of Oxford, where Appleton had set himself up in the electrical laboratory there. Now, Appleton had realized that this fading that he saw with signals was greatest when the transmitter and receiver were about 100 kilometers apart. And so this experiment was set up between Bournemouth and Oxford because it provided about the optimum conditions. You had similar strengths of these two waves and they interfered with each other most clearly. So here we are above Oxford, but if we go back up to space again, we can see the scale of this experiment. It's much smaller than Marconi's experiment, with the path only travelling 100 kilometers across the ground. We can see that there's a ground wave that goes from Bournemouth to Oxford, and there's a sky wave that's going to reflect off the layer. And the maths in Appleton's paper was remarkably straightforward. He likened it to a well-known optics experiment known as Lloyd's mirror, where you could get two paths of light to interfere with each other and cause bright and dark fringes. Well, in Appleton's experiment, it was the radio signal that would get louder or quieter and cause this fading. And he arranged for the radio signal to have a slight change in frequency over the time of the experiment. And as a result of that, he could work out the number of these fading events that he would expect to see, the capital letter N there, where A dashed is the path via the reflecting layer and A would be the distance along the ground. He knows the wavelength lambda, and so from this he could work out what the path difference was. And as a result, he determined that there was a reflecting layer at about 100 kilometers up in the atmosphere. Now, around the same time, two American engineers, Breet and Tuve, had developed a technique for sending brief radio pulses up and measuring the height of the ionosphere from the time it took to reflect off the ionosphere and come back again, so like detecting the echo of the ionosphere. Appleton realized that this technique was something that was going to enable to have a much more detailed probing of these reflecting layers. They became known as the ionosphere, named up by Appleton's colleague Watson Watt. And by varying the radio frequency of each of these pulses, you could make a probe through the whole of the ionosphere and estimate how strong it was at different heights. And this is a picture of the Radio Research Station at Ditton Park in Slough around 1930s, and there's a hut in the background there, hut number 18, where the sequence of ionospheric measurements was started. And by changing the radio frequencies in this way, what you could do is that you could create these layers. So if you think of this is frequency going from right to left rather confusingly on these graphs, and height is the vertical scale. Height was estimated from the time it took for the signal to go up and back from the ground. So some correction is necessary, but it gives you a rough idea of the heights of these layers. And as a result, you can see that there's a lower layer here. This is the layer at about 100 kilometers that Appleton first discovered, but there was another layer above it. That became known as the F layer. Appleton's layer became known as the E layer. And you can see here a double reflection of that single layer. So this was the beginning of a sequence that Appleton started in 1933, and it's still going today. So at the Rutherford Appleton Laboratory in Oxfordshire, there is a digital, what's known as an ionosonde now, an ionospheric sounder. And again, it's producing very similar graphs. So here we have radio frequency along the bottom and height up the side. And this gives you an indication of how strong these ionospheric layers were. The more ions, the more electrons there are in the upper atmosphere, the higher the radio frequency that they can reflect. This is the longest continuous sequence of ionospheric measurements in the world. It started in 1933, continues today, and this is a plot showing monthly averages of the various parameters. So the F layer, the biggest layer, the strongest layer here, is shown in blue. Appleton's E layer is shown in red, and there's an intermediate layer known as the F1 layer in between the two. At the top of the graph there, the black line, that's the number of sunspots, which give an indication of how active the sun is and how bright the X-rays and extreme ultraviolet light are that are creating the ionization in the atmosphere. And you can see that the sun varies with a known 11-year cycle, and the ionosphere follows it. So this really does record in great detail the activity of the sun since the 1930s, so way before the space age. And for comparison, there's a secondary site here. We have Stanley in the Falkland Islands. So that's been going since 1945, but hasn't been quite so reliably running recently. Well, all these records still exist, and I'm very keen to preserve them. They contain so much information. They contain information about the sun, solar activity, space weather events where huge eruptions have arrived at Earth and they disturb our atmosphere and cause the ionosphere to do some quite funky things. They've got records of astronomical phenomena like meteor showers, solar eclipses inside, again, way before the space age. And there's also, because we have a long continuous sequence of these records, we could try and detect a signal from climate change. As climate change greenhouse gases trap heat in the lower atmosphere, the upper atmosphere is expected to cool and contract slightly. So there is some modelling work that's been done to show that the ionosphere should have descended by about 20 kilometres. I'd like to look at these records and find out if that is indeed true. But they're quite complicated things and they're on pieces of paper, so we need to somehow transcribe all this information. And we'd like to set up a citizen science project to enable this to happen. We're having a go at building an interface here where we can look at all the writing that's on the ionograms, and we can get people who are interested to do so to help us to transcribe all these data. And the science we could do with that, if we could, would be amazing. So watch this space. We hope to have a project up and running soon, but it's a big task. There's something like 250,000 of these ionograms to scale. The science within them would be remarkable if we could get all that information off these pieces of paper and make them available digitally to modern scientists and engineers. Well, thank you for listening. I hope this has been a fascinating insight into early radio research, and I could go on about this for days, as I'm sure my colleagues could testify. If you're interested, let me know. I'll try and produce some more information about some of the more detailed events within this data archive. Thank you very much for your time.